Thank you, Raghav. So, okay. Okay, good morning. Welcome to lecture number 24. So, towards the end of last lecture, we looked at implementation issues of Kruskal's algorithm. So, the main issue was how to test if when you add an edge to the forest being constructed or forest being currently being constructed, which is a partial tree, it's not completely tree yet, contains a cycle or not. Okay, so that is the main challenge that we face. So a naive implementation will require conducting BFS on this tree, on this I union EI, and see if there is a cycle or not, BFS or DFS, which would take really bad, I mean, quadratic time, that is order of m into n time, where m is a number of edges and n is a number of vertices. Okay. So yeah, we were looking at ways of implementing this in a better way. So we looked at the disjoint tree data structure, possibility of something which we call as disjoint tree data structure. Of course, we'll in the end call it as disjoint set, because we'll treat them as sets rather than trees. Okay. So you can imagine at any point of time, I is a collection of trees. Okay. In fact, trees on disjoint sets of vertices and hence disjoint sets of edges. Okay. So the way we looked at it is, we'll be at any point of time we'll be maintaining some number of trees. So to begin with, you can assume every vertex is a tree. So you have n trees, and during the process, the number of trees will decrease. So the operations that we need is creating a new tree, create a new tree with the given edge, merge two trees, that is given an edge uv, you take the tree containing u and take the tree containing v, merge them into a single tree. So for this, you also need, given a vertex, you need to locate the tree in which it is contained in. So these are the operations that we would like to support. We took a purely set view on this, so we just pose this as a set theoretic problem, or a problem of maintaining sets, collection of disjoint sets. So what we want is, we want to maintain some number of disjoint sets, S1 to Sk. K is arbitrary, it could be as big as n. So we can assume that the universe is 1 to n, or labeled as, say, x1 to xn. So what we want is, the operations is, given an element x, we need to create a set. We call it as make set operation. So create a new set, let's call it as Sx. Given two elements, we should be able to compute the union of two sets and store it as a new set. Okay. Yeah, so and store it as a new set here. Okay, so given two elements, locate the sets containing those elements. Let's call it as Sx, the set containing x, and Sy, the set containing y. We need to obtain union of Sx and Sy and store it as a new set. So since we want the sets to be disjoint, we'll throw away Sx and Sy. So in place of Sx and Sy, we need their union. Okay. So here the primary point to note is, these sets are disjoint. Okay. So we can always imagine that their union is 1 to n. Okay. I'll tell you why soon. But so for example, in the Kruskal's implementation, right? So finally we want a spanning tree, assuming connectivity of the graph. Assuming that the graph is connected, you want a spanning tree, or even when you have a spanning forest, there will be n vertices, right? So union of these, we want it to be n, at least at the end. So yeah, we'll assume that, I mean, at any point of time, their union is going to be n. So hence they will be a partition. Okay, so that's an assumption which is harmless. Yeah, so typically, one small point is, we usually represent the set by a representative element. Okay, some element in it. In some applications, it could be the least element, least indexed element, or least valued element. It could be arbitrary. It doesn't matter. For our tree example, it really does not matter what the representative is. So we'll not be really bothering much about this representative element. So we'll also see that updating this representative is also not an issue. Okay, so that's not a big deal. So in many applications, I mean, it usually representative has to be the minimum element or maximum element and so on. So in such cases, we will have to do some processing of the representative element as well. But we are not treating it as a separate operation. Okay. Yeah. I hope the problem is clear to everyone. So here we'll make some assumptions. So we'll assume that so total number of operations. Sorry. Total number of operations is equal to m. Okay. So size of the universe is n. So number of make set is n. Okay. So this is just a simplifying assumption. What we do is, so what we assume is initially you have n sets. Okay. So elements 1 to n. So each element is a set. Okay. So then you can actually get rid of this make set operation altogether. So assuming that each make set operation is order 1 time, then this will be order n time. So if each make set takes order log n time, then this will be n log n time. Okay. So this is something mostly implementation. I mean, this is not required per se, but it is harmless. Okay. So this assumption is harmless. So we'll assume that m includes the make set as well. So we'll assume that m is greater or equal to n. Okay. So these are the assumptions. I'll list them formally and the slide following. Okay. So we'll begin with a simple implementation of this disjoint set data structure with the support to all these operations that we posted in the requirement using linked list. Okay. So yeah, so we are going to see a linked list implementation. So this is the statements that I have made, I mean assumptions I have made. So we'll assume that there are n elements x1 to xn. So total number of operations is m. And we'll always assume that there are exactly n make set operations, that is make set x1, etc., make set xn. So, and we'll also assume that all of these are performed in the beginning. Now, there might be an implementation where this does not make this assumption, but it's always easier. So you always see, for example, in the Kruskal's algorithm, right? If you have make set or make tree for x1 to xn, that is n vertices, then in future you don't need any of this, right? Then the only thing that you need is union and find. Okay, so that way you simplify the operations that is required. So then you don't have to make a tree of multiple number of vertices. Okay, so for example here we said make a set with sorry. So he said create a new tree with a given edge. So we don't have to do that. So you create trees with single vertices, then you got rid of this operation. Okay. Okay. So yeah, so I took this picture from CLRS. So this is a linked list implementation. Okay. Yeah. So what we do is, so we treat each set as a linked list. Let's say we have two sets, okay, S1 and S2. So each is a linked list. Now, how are the pointers? So this linked list, so you don't have to assume any ordering of the elements. So the elements, say FGD are the elements of S1. Then you have a linked list where the head points to F, then F points to the next element, that is G, and G points to the next element, D. Okay. And we also have a pointer for tail. This is just for convenience. Okay, so that is the one that points to null. Okay, so D will be pointing to null. And we'll also assume that each element here, it also points to its parent. That is the set it contains. Okay, so there is a back pointer for each of them. So let's call this as parent. This is next. Okay, so this is null. Okay, so S2, let's suppose it contains C, H, E, B. No ordering is assumed, so we don't assume any ordering of the elements. So some arbitrary linked list. Okay, so the only important point is each element here is pointing backwards. So the way you implement is, so suppose our array looks like this. Okay, so how many elements are there? 3 plus 4, 7, right? 1, 2, 3, 4, 5, 6, 7. So I can erase this portion. Okay, so ignore this portion. So let's say this is C, D, E, F, G, H. Okay, I missed B. Okay, so B. Okay, so now there are two sets, S1 and S2. So please stop me and ask questions. Okay, so because I can't see your faces, I can't see the feedback either. So please don't hesitate to ask questions. Okay, so F, G, and D will be pointing to S1. So F, G, and D will be pointing to S1. The remaining will be pointing to S2. Okay, now it has head and tail. Okay, so now there will be next pointer. So this is a parent pointer, and this is next pointer. Let's say. Okay, so here the next pointers will be F will be pointing to G, G will be pointing to D, D will be pointing to null. Okay, so similarly for the other, that is C will be pointing to H, H will be pointing to E, E will be pointing to B, B will be pointing to null. Okay, this is how it will look like. Now, so head will be pointing to F here. So let's use a different color. Head will be pointing to F here. Tail will be pointing to D. Okay. Similarly for S2. Okay. Yeah. So what we assume is, so if you want to access element D, so we'll assume that it's unitime operation. You know the index of the array. Okay. So I mean, you just assume D represents this position as well. Okay. So when I say, okay, so give me the set containing D. How will I do? I look at D and look at its parent pointer. So that is S1. Okay. So that is, so what I do is, so if this is stored as an array, so I just access this element in one axis, right? So you're just looking at the pointer here as say D dot parent will give me the set containing it. And if I want to know the set containing say G, okay, same way you look at G and look at its parent pointer. Okay, so what we assume is, so in this implementation we are assuming that the elements are stored in an array. So accessing one element. So given X, accessing it, its position is unit time. That is accessing the pointers corresponding to it. That is parent as well as next pointers. It's unit time operation. Okay, so that is the assumption. Yeah, so we'll take one more example just to be concrete. So I'll take questions, if any.
Sir, each of these elements F, G, D, are these the vertices of the tree or the edges?
So no, there is no tree here, right? I mean, you're seeing this as sets, right?
No, I meant in like analogous to Kruskal's
You mean
algorithm.
Kruskal's?
Yes, yes.
So Kruskal's, so see, this is just vertex. You can just imagine it as vertex.
Okay, sir.
Well, I mean, for Kruskal's, we also need to store edge. That portion we have thrown off, okay? Because see, all we need is, we don't really need the edges right away, right? If you think, for each component, that is each tree in the forest, what are the vertices there? That is all I need to know, right? For our implementation.
Yeah. Yes.
Because when you get a new edge, you want to know if it is within the same tree or not. If it is within the same tree, you know that it is a cycle. So for our purpose, we only need to know the vertices. You don't have to take care of the edges here, right?
Yeah. Okay, sir.
Yeah. Yeah, so if there are no questions, we'll see one more example just for that. Yes, yes, yes.
Yeah, you were saying something regarding that we need not worry about the edges. I did not understand that
Yes.
part.
Yeah, so in this implementation, right, I mean, for this disjoint set data structure, we don't have to worry about edges for Kruskal's algorithm. See, you have to keep track of edges for outputting, okay? But the way we look at it, right, so how do you detect a cycle? You just need to know the sets of vertices in each component, right, each tree. That's all you need to know. You don't have to know the edges there. So for this data structure, it only needs to care about the vertices. That's all. To detect the cycle here, what do you need to know? You need to know in each component what are the vertices, right? Say this is one component. Sorry. This is one component, and this is one component. So you just need to know the which of the vertices. So when you get an edge, you want to see if the edge is within a component or it is outside of the component. So this way. So for that, that is why we took this set view. When we took the set view, the edge relation is ignored completely. So for this implementation, we don't care about edge. But for Kruskal's algorithm, you need to keep track of edges. That is it. In the end, you need to output the edges. So yeah.
Sir, okay, can we go to the latest slide? That is the last slide.
This one, right? Yeah.
Yeah, okay. Here, did we discuss how we are obtaining S1 and S2?
No, what do you mean by obtaining S1 and S2?
We have said that we have disjoint sets which have make set function, union function, and find function.
Mm-hmm. Mm-hmm.
Okay. If we are given a set of vertices,
Mm-hmm.
how do we form these sets, these disjoint sets using
No,
those?
that will come to. I mean, okay. How do we form? We'll see it fairly easily. But the representation, is it clear? So this is
Yes.
how we are going to represent.
So that finding the set corresponding to any element will be easier, you are saying.
Yes. So we'll discuss each of the operations now. Okay. So we'll discuss each of the
Okay.
operations. So yeah, in the next example, I'm going to demonstrate all of that. But the view is this. Okay. At any point of time, you need to store sets. Suppose these are the two sets. How do you store it? So all of the elements, they occur in an array. Okay. So each array element will be pointing to the corresponding set, which is basically two pointers, head and tail, which is a linked list, in fact. Okay. So we'll assume it is a single linked list. Okay. And so yeah, so that is the interpretation. Okay. Now, how do we construct? We'll come to that. Okay. Okay. So let's suppose you have 11 elements. Okay. So my universe is 1 to 11. Okay. So now I'm going to demonstrate the sequence of operations that you're going to do to construct these three sets. Okay. So at the end, we'll stop at these three sets: S1, S2, S3. Okay. So we said initially we have, so n is 11, right? So we'll have 11 elements. Okay. So there is one more missing here. Okay. So I should have taken 10 here. Sorry. 1, 2, 3, 4, 5, 6, 7. Okay. I'm missing a lot of elements here. Okay. So maybe that's no problem. It will be S4 is, let's say, what are the missing elements? 8, 9. Okay. Okay. So initially, what we do is we'll have, so 10 make set operations. Okay. So we construct the sets 1, 2, etc., etc., 10. Okay. So now what are the operations that we need to construct S1? Union 1, 5. This resulting set in union with union 7. This gives me 157. So we needed two union operations here. This is for S1. For S2, union 2, 3. That's it. That gives me the required set. For S3, union 4, 6. This union with 10. Similarly for S4, union 8, 9. Okay. So how many union operations were required? 1, 2, 3, 4, 5, 6. 6 union operations. Okay. 6 union operations. So in the case of Pruscal, you'll go on until you have the spanning tree. So if the graph is connected, it will be single set. Okay. So the way we are going to imagine is you have n elements. So initially you are going to have n make set operations. So this is n here. Okay. Which gives you singletons. So there will be n singleton sets. So after that, there are some m, say m minus n operations. Let's call it as m itself. Okay. M operations, which could be union as well as also find. So we ignored find here. We didn't put find here. So how the way it will happen is I construct union of 1 and 5. So this gives me 1, 5. Then I need to do union of these two. So in that case, what I'll do is, so I'll do a find of say 1 or find of 5 and then find of 7, then do the union. Okay. So similarly here I'll do a find of 2 and then find of 3, then take the union. So again here find of 4, find of 6, take the union. Then I either find of 4 or find of 6 and then find of 10, take the union. Okay. So that is how we'll be using it even for Kruskal's or in general. Okay. So yeah, so let's make a couple of observations here. So with this assumption, so nowhere in between you are going to have make set operation. Okay. So number of make set operations is equal to n. Okay. So what can you say about the number of unions?
n minus number of components.
N minus number of components. Let's assume components is 1. In that case, n minus 1, you're saying, right?
Yes, sir.
Yeah. So so you don't have to think in terms of the graph itself. I mean, you can just think in terms of term, because I mean sets, because this is a more general structure than just for cruscals, right? Yeah. So did everybody get it? Why is that number of unions can always be bounded by n? Because when you do union, the sets are going to be disjoint, right? Remember that. So the way we are implementing it, so when you take union, you are going to destroy these two sets. These two sets are gone, because otherwise the sets will no more be disjoint, right? If I keep 1 as well, see, when I take union of 1, 5, I get this new set 1, 5, but 1 and 5 are destroyed. They are no more sets for us. Okay. So that way, if you look at the number of unions, since there are only n elements, so to begin with, there are only n sets. How many disjoint unions can you do? At most n. So in fact, it could be even n minus 1, right? You can't do more than that, right? Because every time the size increases. When you perform a union, the size increases and the number of sets decreases. Initially, you had only n sets. In the end, you can have at most 1 set, right? So you cannot perform more than n union operations. Okay, so this is just an observation. That's all. This is basically the consequence of assumption that the sets are disjoint. If I were allowed to keep 1 and 5, can have arbitrary number of unions. Okay, so yeah, but that is not the case. So the way we are implementing, we want disjoint sets. In fact, if you don't have disjoint sets, yeah, you cannot really have fairly efficient than what we did with BFS kind of thing. Okay. Yeah.
Sir, it's strictly less than n.
I think it's you can bound it with the n minus 1, right?
Yeah, it's less than or equal to n minus 1, so it's strictly less than n.
Yeah, it's actually strictly less than 1. I'll just take it as n. Yeah, because n minus 1, you can just imagine it as a binary tree kind of, right? Every time you're constructing. So at the top, it will be like 1 to n. At the bottom, these are singleton sets. So you can have in a binary tree with n leaves, how many internal nodes you can have? N minus 1, right? So this will be in fact n minus 1. At most n minus 1. So it's less than or equal to. Yeah. Okay. Okay. So let's just demonstrate a few iterations of this just to understand what is a complexity. Okay. So what I'll do is I'll take this array. So 1 to 10. 1, 2, 3, 4, 5, 6, 7, 9, 10. Okay. So I'll not start from the beginning. I'll take one configuration and demonstrate how to do union. Okay. So in fact, I have the example from the CLRS. Maybe I'll use that. Okay, that's better. Okay. Okay. So let's draw this configuration: S1, S2, S3, S4. So S1 is 157, right? So S1. So I have 1, 5, 7. So in origin, I mean reality, we'll be having pointer this way. So 1 to 5 and 5 to 7, 7 to null. Okay, so this is how it will look like, but we'll just draw for convenience like this. This is 7. Sorry. Okay. Now S2 is what? Can somebody tell me if you remember? 2, 3. S3 is 4, 6, 10. So 2, 3. This is head, this is tail. This is head, this is tail. This is head, this is tail. Okay. S3, 4, 6, 10, right? S4 is what? There are two elements, I think 8 and 9. Is that right? 8 and 9. Okay. 8, 9. Okay. So there are head and tail pointers. So tail here, like this, tail here, like this. And there are always parent pointers which point like this. Okay. Yeah, sorry. Okay, so let's demonstrate some operations now. Okay. So let's say find 7. So how will you do it? So output 7.parent. I'm just misusing this. I should have said, okay, the corresponding array index and so on, but I'm not bothered about language implementation. So as long as we understand, that's good enough. So all we need to do is we just look at the element 7 and take its parent pointer, right? So find operation, if you look at it, it takes unit time, right? So we'll take this as unit time. Order 1. So in cases where you need to have representatives, so in that case you will have to access 7.parent.representative. Okay, so the representative element of the set containing 7 is going to be 7.parent.representative. Okay, so this will be like 2 indirect accesses, right? Still order of 1. So 7.parent is 1 access, and then from there you have to access again. So there are 2 level indirect access. So we'll treat it as order of 1 operations.
Sir, when you say output 7's parent, is it just the representative element or the entire set?
So see, here we didn't really implement the representative set as such, right? Element as such, right? So in that case, it's just this pointer. This, I mean, whatever. So if you are implementing in C, this will be a structure, right? So this structure, pointer to this structure. That's it. Okay. So this structure basically consists of 2 pointers, head and tail. Okay. In case implementation also requires representative element. So in case if you want the find to return the representative element, so in that case you'll have to have one more access. So from this structure you access the representative elements. That is 7.parent dot whatever representative, let's call it as. So that will again be constant number of accesses, right? So 7.parent is one access, and then whatever seeking the representative element, that's again one more access. So we'll just treat it as unit time or order of 1 operations.
Okay, so it is different from printing the entire set containing 7.
No, you're not printing the entire set. No. Yeah.
No, I'm not saying printing, sir. It is different from accessing the entire set containing 7 because it would be order. It could be order of n.
Yeah, the size of the set. Yes. No, you're not accessing the entire set. No.
Okay, I understood, sir.
Yeah. Okay. So now let's say what I want is union.
Hello, sir.
2, 4. That is union of sets containing 2 and 4 respectively. That is set containing 2 and set containing 4. So in case they belong to the same set, then no change. Okay. So in case, so the non-trivial work is to be done only when they belong to 2 different sets. So what should be the outcome? So the outcome should be union of these 2 sets. So you need to we need to replace S2 and S3 with a new set. Let's call it as, let's say, S5, which contains union of these elements, that is 2, 3, 4, 6, 10. So how will you do it? First find 2 and then find 4. Say this is pointer P1, this is pointer P2, other pointers. Yeah, so please help me. So how will you do it?
From S3, make all the parents of each node as S2.
Okay, so maybe let's go it sequentially. So you need to merge the linked list, right? So append the linked list, right? So shall we do that first? So that's easier. So you make this point to here, right? So set S2 dot tail as S3 dot head, and then update parents of each element in S3. That's what you said, right?
Yes.
S3. Okay, so how do you do that? So first thing is you need to merge the list. That is, make this pointer. So this null pointer is gone now. Okay, so the null pointer is gone. You make it point to the head of the set S3. That is set containing 4. So that is head of P2. Okay, so that is, so in technical terms, this is P1 dot tail is equal to P2 dot head. Now you need to update the head for the elements in S3. So how do you do that? You access this linked list one by one and you update them. So you remove these pointers and update. This points to this now, this points to this now, this points to this now. Okay.
Hello?
Yeah.
Sir, it should be, I think, p1.tail.text.
P1 dot, yeah, tail dot next. Yeah, you're right. I'm sorry. Yeah. So P1 dot tail dot next. Yeah. Yeah. So you're yeah. There is one more thing that we need to do. So we also need to have P1 dot tail is P2 dot tail. The tail has to be updated accordingly, right? Now this is no more the tail. Yeah. This is it. Okay. Yeah. Yeah, so there is one limitation with the way I'm writing. Okay, so this board, right, only the last thing gets saved. Okay, so this somehow I don't know how to save. So in the video you can see the changes, but in the slide you'll see only the last thing. Okay, that's a limitation with this. So yeah. Okay, is it clear? So the only non-trivial part is updating the pointers. Okay, so updating the pointers of the second set or first set, that you can decide. Okay, so that is all. So the find operation takes order one time. So union operation potentially can take size of one of the sets. So time could be size order of, sorry, order of size of S1 or S2, whatever, or S3, in this case S3. Okay, so unless you access the list you will not know the size. So that way, I mean, it could be the worst case. We can end up with, say, the larger one always, updating the larger list always. Okay, I'll just demonstrate the union once again using the example I had from CLRS. Okay, so this is how it will look like. This is drawn much neater than what I did. Okay, so you had S1 and S2 to begin with. This is the sets. Okay, so the union is basically you update the pointer. So the tail here points to the head. This, so that is D would be pointing to the head C here. Okay, then here all parents should be updated. So to S1. Okay, now S2 is gone. This is how it will look like. And now finally you need to update the tail of S1 to the tail of S2. So this is what. Okay. Yeah, is it clear? So the make set operation, right? How complicated is it? So we are making only singletons at the beginning, if you remember, right? So how complicated is it? You just create a structure. Say, assume you are going to implement in C, any language, any equivalent language. So you have to create a structure which consists of 2 pointers, possibly one more representative element value. So you just create, which is constant size operation. I mean constant time operation. You'll have to allocate memory to whatever required. That is 2 pointers and 1 data, whatever. And then point to xi, and xi should be pointing to si. Okay, so these are all order 1 operation, order 1 time operations. Okay, so overall you require order n time implementing this. Okay, so yeah, so for find operation it is order n time. So this is something off the track, I mean off the shelf. Okay, so you're not really thinking about it anymore. So the only non-trivial part that we saw were so find and union. So find how much time it takes. We already saw that. You just have to access 2 pointers at most. So it is order 1. So union is the one which is non-trivial. Okay, so union is the one we need to analyze. What is in the worst case? Yeah. So any questions on implementation of this? We'll analyze the time now, but is it clear how this is done?
Hello, sir.
Yes, yes.
So the data is in the form of an array.
Yeah, so that is the easiest way to
In the
implement,
form of
right? Yes.
list. Hello.
Yes. Sorry.
I'm not understanding this part. So your data is in the form of an array.
Yes.
And then suppose if you want to do find of 7, then how am I like, okay.
So you can imagine, so data, so you have an array, but it's a structure array. Okay, so it has 2 pointers as well. So say 7th element has 2 pointers. So one is parent, one is the set it belongs to. What was that? Next. Okay. So one is parent and one is next. So you can just imagine.
It's a struct pointer. Okay.
That's the easiest way to implement, right? Otherwise, you'll have an array, then how do you locate? So you'll have to locate the particular node and so on. So you can just imagine this is an array of structure array. That's all.
Okay.
Yeah.
Sir, also if we want to find 7, first we have to search in the array. If we
So
want
that's
to,
what I'm saying. This search has to be made trivial in the sense that it should be indexed properly. That's what I'm saying. So when I say 7, if I look at the 7th element in the array, I should get it. That's it. That should be unit time operation. You should not be doing a search. Then it becomes expensive, right?
okay, sir.
Yeah, so that is the assumption that we are making. Okay, so you actually have this array. So these elements are in an array. So when I say 7, okay, find 7, I can locate the pointer parent as well as the next element for array in unit time. Okay, that is important. Otherwise, otherwise it depends on how do you store these elements and so on. You may have to do a binary search and so on. That is not what we want. Okay. So for that, the penalties, you'll have to store these elements and as well as these explicit pointers. That is fine. Now, I mean, you're not copying. So when I say S1, you're not copying these elements. You're just making this pointer adjustment. So 1 points to 5, 5 points to 7 within the array itself. Okay.
Sir, so are we storing in a like in this example 1 to 10 numbers? Are we storing in a sorted format?
Yeah, we'll have to, right? Otherwise, how will you do indexing? So that it has to be properly indexed. That's all. So when I say element 100, I need to know which location in the array to look at. So best way is to sort. If you have different labels, right? So elements having different labels, then maybe you sort them and rank them. So you should know that rank of each element. Otherwise, you can't access, right? So best way is to treat elements as 1 to n. So that when I say, okay, find I means I have to look at the ith location in the array.
So can we use hash map for finding the element because the elements may not be in the consecutive order like.
See, you can do that, but I mean, at least for our immediate application for graphs, right? What is R numbered 1 to n, right? So that way you don't have to worry. Otherwise, yeah, you can have a simple hashing. Okay, so what you would do is like, but even then, how do you do? See, you'll have to do binary search, right? Even then, when you do hashing. So when I say find 100, its location. If its location is not 100, then we'll be in trouble, right? You'll have to do a binary search, right?
Yes, sir.
Yeah. So even if you do hashing, because you'll have to take the inverse of that hashing, right? So that is not trivial. That's not trivial. So yeah. So in such applications, I mean, you'll have an overhead there. But in our assumption, so we'll assume that elements are 1 to n. So you can have an array of size n. So in that case, find operation is unit time. Okay. So that is what the statement is. Okay. Good. So this is what we had discussed. So this is an English description of whatever I stated, verbal description. So you store x1 to xn in an array along with a pointer to the set which they belong to, which we call as parent. For each set, we include a pointer to the head of the list and as well as the tail of the list. Okay. So the set is being stored as a linked list. Okay. So make set, yeah, it's trivial. So given an element, what you do is you create a structure with the 2 pointers, head and tail. So both pointing to x. Okay. Set x next as null. That's it. Okay. So this is order 1 time operation. Okay. Yeah, so total time is order 1 per mix set. There are n mix sets. Therefore, total order n time. Okay. So here we are assuming that accessing one memory location is unit time. Okay. So that's it's essentially accessing and setting the pointer. All of these are unit time. That's what we are assuming. Okay. Now same thing with find operation 2. So given x, all I need to do is I have to get x dot parent. I'm just misusing the notation. I should be like, so if A is the array which stores this element, it should be A of x dot parent. Okay. So since we are not writing the code, we are not so particular. So x dot parent is a parent pointer. So you need to basically access how many one so one direct access and one indirect access, right? X dot parent is okay. There's no indirect access if you don't want the representative elements. Otherwise, there are 2 accesses, one direct and one indirect. Okay. So again, this will be order 1 number of operations, order 1 operation.
Sir, what do you mean by indirect access?
So if you want data from the parent, right? So that is an indirect access, right? So say if you have a representative element and you want to access it, so how do you do that? You will have to have an indirect access here, right? star of whatever, x dot parent.
Okay, you go to the parent and then search for it.
Exactly. That is when you need representative elements. If you don't need representative elements, it's just x dot parent. So order 1 operations.
Okay, sir.
Yeah. Yeah. Or in fact, order 1 time. I mean, assuming operations take unit time, accessing the memory or assigning pointer, all of this. Okay. Yeah. So now the non-trivial part is union. So given x and y, locate the sets containing these elements, say sx and sy. So this is find operation. So this is order 1 time. Sorry. Okay. Now you locate the tail of sx and make it point to the head of sy. Order 1 time. There is also one more point which I missed. That is set tail of sx to that of sy. Okay. This is also order 1 time. But this is the non-trivial part. So this can take order of size of sx. So in the worst case, it will be max because we don't know the size. We might end up picking the larger set always. Max of size of sx, size of sy. So that is a non-trivial part. So if you want to say, let's look at the Kruskal's implementation. So you will have n-1 union operations, right? So what can be the worst case complexity? Total. Let's take the following. Okay, so you have make set. So I'll just use make. Okay, make x1 etc. make xn. Then what I do is, so union x1 x2. Okay, then union x3 x2 union, sorry, union x4 x3 and so on, union xn minus 1 sorry xn minus 1. Sorry. So what will be the time required? So let's assume that the protocol is we always take the right set, the second parameter, and update its pointer. Okay. So now the size will be size of the set containing x2. Here the number of operations will be size of the set containing x2, size of set containing x3, and so on. Okay. So can somebody tell me what are these numbers? So here it is 1. Here size of x2 is 2, so order of 2. Here it will be order of 3, and so on. Here it will be order of n minus 1, right? Because the right hand side set will contain x1 to xn minus 1 in this case. So if I stop at say iteration I, if I consider say union x I plus 1 xi, so here the size of the set will be I. Okay, so total time will be, so make set order 1 n times, so this should be xn, sorry, so order n for make. For union and find it will be, so find order 1, so it's basically order n together. So for union it will be 1 plus 2 plus etc. plus n minus 1. This could be as well order n. So again there is an order, I'm just hiding that. put order here. So plus order of n into n minus 1 by 2. This is order of n square. So together, in the worst case, our algorithm or implementation, if you are doing n union operations, you can come up with an example. So this is our example where the number of operations is order of n square. Okay, or if you divide by the number of union operations, which is n in this case, or n minus 1, so it will be n per union. Okay, yeah. So we'll see in the next lecture how to save this. So by simple modification here, if you know the size, right, you can always ensure that you update pointers for the smaller set. In that case, it will save a lot of time. You can improve this to order of n log n. We'll see that in the next lecture. Yeah. Okay, thank you. Raghav, please stop the recording. Yeah.
Sir, you were saying something regarding union per